Hello students, I welcome you for this new lecture on conservation of momentum, equilibrium of a particle and common forces in mechanics, which is a part of chapter number 5 titled Laws of Motion. In the previous lecture, we studied about three laws of motion, that is the first law, second law and third law of motion. And the second and third law of motion led us to an very important consequence, that is the law of conservation of momentum. For example, when a bullet is fired from the gun, the force on the bullet by the gun is F, vector F, and the force on the gun by the bullet is minus F according to third law. So in this system, that is a system with no external force, mutual forces between pairs of particles, that is the gun and the bullet, can cause momentum change in individual particles. But since the mutual force for each pair are equal and opposite, the momentum changes cancel in pairs and the total momentum remains unchanged. This fact is known as law of conservation of momentum. We will study this in section 5.7, and in section 5.8 we will study about equilibrium of a particle followed by common forces in mechanics. In the end, we will solve short answer type question. I welcome you once again. Conservation of momentum. The law of conservation of momentum states that the total momentum of an isolated system of interacting particles is conserved. We know that the second and third law of motion lead to an important consequence, the law of conservation of momentum. Take a familiar example. A bullet is fired from a gun. If the force on the bullet by the gun is F, the force on the gun by the bullet is minus F, according to the third law. The two forces act for a common interval of time delta t. According to the second law, F delta t is the change in momentum of the bullet and minus F delta t is the change of momentum of the gun. Since initially both are at rest, the change in momentum equals the final momentum of each. Consider two bodies A and B. Initially momentum PA and PB. The plural of momentum is momenta, PA and PB. The bodies collide and get apart. With final momentum P-A and P-B respectively. By the second law, vector FAB delta t is equal to P-A minus PA. And F of B on A delta t equals P-B minus PB, where we have taken a common interval of time for both the forces, that is delta t is common for both, that is the time for which the two bodies are in contact. By the third law, vector F AB, that is force due to A on B, is equal to minus of force of B on A. Therefore, momentum P dash A minus momentum PA equals minus P dash B minus of PB, where PA and PB, P dash A and P dash B are momenta respectively. That is, rearranging, we get PA plus PB equals P dash A plus P dash B, which shows that the total final momentum of an isolated system equals its initial momentum. Please note, total final momentum equals its initial momentum. Next, we will take up equilibrium of a particle. Equilibrium of a particle in mechanics refers to the situation when the net external force on the particle is zero. According to the first law, this means that the particle is either at rest or in uniform motion. Please see the figure which shows equilibrium under concurrent forces. If two forces F1 and F2 act on a particle, equilibrium requires that F1 is equal to minus F2. You see, F1 is from left to right and F2 is from right to left in the figure above. Let this equation, that is F vector F1 is equal to minus vector F2, be equation 2. That is, the two forces on the particle must be equal and opposite. This negative sign indicates opposite. Equilibrium under three concurrent forces F1, vector F1, vector F2 and vector F3 requires that the vectorial sum of three forces is 0. Please see the figure above once again. Vector F1, vector F2 and vector F3 act on the particle. That is, three vectors are acting on a particle, and equilibrium requires that their vectorial sum should be 0. The vectorial sum is shown in the triangle. Therefore, F1 plus F2 plus F3 equals 0. We added vectorially. Equation 3 implies, this equation implies that the respective components along the x direction, F1x plus F2x plus F3x of each of these forces must be 0. Similarly, F1y in the direction of y, F1y plus F2y plus F3y should be 0. The third direction is z direction. Similarly, F1z plus F2z and plus F3z equals 0. Please note that in these equations, vectors are not shown because the directions are indicated by x, y and z axis. So, F1x, F1y and F1z are components of F1 along x, y and z directions respectively. Let us solve a problem associated with equilibrium of a particle. Question number 6. A mass of 6 kg is suspended by a rope of length 2 meters from the ceiling. A force of 50 newtons in the horizontal direction is applied at the midpoint P of the rope as shown in the figure. Find the angle that the rope makes with the vertical in equilibrium. Take G is equal to 10 meters per second square. Neglect the mass of rope. Please see the figure. The given problem is explained here. In figure A, this is the ceiling and this length is a rope of 2 meters. It is given. This length is 2 meters and it is given a force of 50 Newton is applied at point P. 50 Newton is applied at point P. And the angle, so because of this 50 Newton force, the rope bends and makes an angle theta with the ceiling as shown in the diagram. W is the weight, 6 kg weight suspended from tied to the rope. We have to find the angle theta that rope makes with the vertical in equilibrium. It is given that the value of G, gravitational force, is equal to 10 meters per second square. Neglect the mass of the rope. Rope's mass is to be neglected. Figure B and C are the free body diagrams of the equilibrium of a particle. B and C are called the free body diagrams. So here the tension, this W acts at this point P, this is point P, and W acts downwards and T2 acts vertical forces, and horizontal forces also are shown. So the three tensions acting at the point P are shown in this figure C. So at point P there are three forces, three tensions. One is T1 due to the rope tied to the ceiling and 50 newtons acting horizontally and T2 acting downwards. Let us solve it. Consider the equilibrium of weight W. Clearly, T2 is equal to, T2 is equal to m into G, mass into gravitational force, that is equal to 6 into 10, that is equal to 60 newtons. Consider the equilibrium of point P under the action of three forces, tension T1, T2 and horizontal force 50 newtons. The horizontal and vertical components of the resultant force must be calculated separately. So therefore, T1 cos theta. If you consider the third figure, this is T1 cos theta, red line. So T1 cos theta should be is equal to T2, that is the vertically acting downward, that is equal to 60 newtons as per the figures. Figure B. The T1 cos theta is equal to T2 is equal to 60 newtons. Resolving the horizontal component, we know T1 sin theta. T1 sin theta acts here horizontally. So T1 sin theta is equal to 50 newtons. That is acting from the point P to right hand side. Let it be equation 2. Therefore, equation 2 by equation 1 is equal to T1 sin theta by T1 cos theta. That is equal to 50 newtons by 60 newtons. That is equal to, we know T1 and T1 gets cancelled. Sin theta by cos theta from the knowledge of trigonometry equals tan theta, that is equal to 5 by 6. So we have to find theta by taking tan inverse. Therefore, theta is equal to tan inverse of 5 by 6. That is equal to, from tables, 40 degrees. That is the answer. In mechanics, we encounter several kinds of forces. The gravitational force is, of course, pervasive. Every object on the earth experiences the force of gravity due to the earth. Gravity also governs the motion of celestial bodies. The gravitational force can act at a distance without the need of any intervening media. Please see the figure on the right hand side. This is the surface of the earth and a body is falling. It is a falling body and there is a gravitational force between these two which is acting downwards. The body is not in contact with the surface. Contact forces in mechanics. So where a contact force on an object arises due to contact with some other object, solid or fluid. When bodies are in contact, please note are in contact. Example, book resting on a table, a system of rigid bodies connected by rods, hinges, and other types of supports. There are several contact forces for each pair of bodies satisfying the third law. Normal reaction. The component of contact force normal to the surface of the contact is called normal reaction. Please see here, this is an object is kept on the table and there is a contact normal force acting downwards and reaction is vertically up. So the component of contact force normal to the surfaces is called normal reaction. Friction. The component parallel to the surfaces in contact is called friction. Please see the figure at the bottom row, middle figure, frictional force. Friction, the body is sliding down, moving down, and there is the force opposing the downward movement of body is friction force. The friction force is shown in the red color, and the force due to body movement is on the blue in the blue color. Buoyant force. Buoyant force arises when solids are in contact with fluids. For example, a solid immersed in a fluid. There is an upward buoyant force equal to the weight of the fluid displaced. This is shown in the middle. This is the buoyant force in the figure. Spring force and tension in the string are two types of other forces. When a spring is compressed or extended, here the spring is extended. So a weight is hung, the spring is connected, fixed to the ceiling, and the object is hung on the other side of the spring. A restoring force is generated. This force is usually perpendicular, proportional to the compression or elongation for a small displacement. So you see, when a body is hung, there is a small displacement. This spring force F is written as F is equal to minus K into X, where X is the displacement and K is the force constant. The negative sign denotes that the force is opposite to the displacement from the unsteady state. You see, this force is acting upwards, displacement is downward. For an inextensible string, the force constant is very high. So here, instead of spring, if you are simple attach a string to a body and the other end is on the ceiling, then there is a tension between the body and the body. The body is connected to the ceiling through a string. Hence, there is a tension. The restoring force in a string is called tension. It is customary to use constant tension T throughout the string. This assumption is true for a string of negligible mass. Viscous force and air resistance, etc., are the other examples of contact forces. In chapter 1, we learned that there are four fundamental forces in nature, that is electromagnetic force, gravitational force, weak nuclear force and strong nuclear force. Only gravitational force and electrical forces are relevant in the context of mechanics. These we will study in subsequent sections. Friction plays a very important role in our daily life. Objects on a table, static objects, and bodies in motion regularly experience friction. When two bodies are in contact, each experiences a contact force by the other. Friction, by definition, is the component of contact force parallel to the surfaces in contact which opposes impending or actual relative motion between the two surfaces. The term impending motion means motion that would have taken place but does not actually take place under the applied force if friction were absent. The figure on the right hand side shows two types of friction. A is static friction and B is kinetic friction. Figure A shows a block resting on the tabletop with a gravitational force G downwards balanced by a normal force N. When a force Fa is applied as shown in the diagram, the block attempts to move towards right. In response, a frictional force Fs is developed, which balances applied force Fa. This force Fs is called the static frictional force. The block actually does not move. It is found experimentally that the limiting value of static friction Fs maximum is independent of the area of the contact and varies with the normal force N approximately given by the relation Fs maximum is equal to mu s times N. Let it be equation 1. Where mu s is the constant of proportionality depending only on the nature of surfaces in contact. The constant mu s is called the coefficient of static friction. The law of static friction may thus be written as Fs maximum is less than or equal to mu s into N. Let it be equation 2. Kinetic friction. Figure B shows that as we increase Fa, the magnitude of Fs also increases, but still the block does not move till Fa reaches a certain magnitude when the block starts moving towards rightwards direction. Here this arrow shows the direction of motion. The frictional force that opposes this motion is called kinetic frictional force Fk. Fk is equal to mu k times N, where mu k is the coefficient of kinetic friction. These are the equations between force static friction and kinetic friction with reference to the coefficient, their respective coefficients mu s and mu k as well as normal force. Properties of friction. If the body does not move, then the static frictional force Fs and the component of F that is parallel to the surface are equal in magnitude, and Fs is directed opposite to that component. If that parallel component increases, magnitude of Fs also increases. Property number 2. The magnitude of Fs has a maximum value Fs maximum that is given by the relationship Fs max is equal to mu s into ns. If the component of F that is parallel to the surface exceeds Fs max, the body slides on the surface. Property number 3. If the body begins to slide on the surface, the magnitude of the frictional force rapidly decreases to a constant value Fk given by the relation Fk is equal to mu k into n. Mu s, mu k are described are as described earlier in this section. After learning the theory part of friction, let us take up some worked examples. Question number 7. Determine the maximum acceleration of the train in which a box lying on its floor will remain stationary given that the coefficient of static friction between the box and the train's floor is 0.15. Here, a box is kept on the surface of the train which is moving. So, we have to find the coefficient of static friction between box and the train as the box is stationary. Answer. Since the acceleration of the box is due to static friction, we will use the formula ma is equal to Fs, which is less than or equal to mu s into n, where m is the mass, a is the acceleration, that is equal to Fs is the static frictional force, and mu s is the coefficient of static friction, and n is the normal. We know that n is equal to m into g, that is mass into gravitational force. G is the gravitational force. Therefore, ma is equal to mu s into mg. So, substituting the given values, we get A maximum is equal to mu s is given as 0.15, and we will assume the value of gravitational force as 10 meters per second square. So we will get the answer A max is equal to 1.5 meters per second square. Next question. A mass of 4 kgs rests on a horizontal plane as shown below. This is the shown figure, given figure. The plane is gradually inclined until an angle theta is equal to 15 degrees. So this plane on which the mass rests is moved to achieve an angle of 15 degrees with horizontal. OA is the horizontal, OB is the inclined plane. The mass just begins to slide. This mass, blue colored mass, starts sliding. We have to find the coefficient of static friction between the block and the surface. So we have to find mu s between the block and the inclined plane AB. Let us solve it. Answer. Resolving the weight mg along two directions. We know the force mg due to weight acts downwards. Weight of the box acts downwards, mg. So we have to resolve this force into two components. Horizontal component, that is mg sin theta, which is shown in the left side, marks arrow left, mg sin theta, and vertical component mg cos theta. Therefore, from the knowledge of trigonometry, mg sin theta is equal to horizontal component is equal to Fs. Mg is pointing towards left and Fs is toward the right. Let it be equation 1. Now vertical component mg cos theta is equal to the normal force N. So let it be equation 2. As theta increases, self-adjusting force Fs increases until theta is equal to theta max. So Fs achieves its maximum value, that is Fs max is equal to mu s into n. Let it be equation 3. Now dividing the equation 1 by equation 2, we get tan theta max. Therefore, mg sin theta by mg cos theta, mg and mg get cancelled, and sin theta by cos theta is tan theta max. It is written here. Tan theta max is equal to Fs is mu s into n. Mu s into n by n is equal to mu s. Therefore, tan theta max is equal to mu s. That let it be equation 4. That is, if you want to calculate the value of theta, theta max is given by tan inverse of mu s. This is from our trigonometric knowledge. Therefore, when theta becomes just a little more than theta max, there is a small net force on the block and it begins to slide. Note that theta max depends only on mu s and is independent of the mass of the block. Therefore, theta max is equal to, it is given 15 degrees. Theta max is equal to 15 degrees. And from equation 4, substituting the value of theta max in equation 4, we get mu s is equal to tan theta, that is equal to tan 15, that is equal to, from the tables we get tan 15 is equal to, value of tan 15 degrees is 0.27. That is the answer. Now let us solve next problem. Question number 9. What is the acceleration of the block and trolley system shown in the figure? This is the figure shown. If the coefficient of kinetic friction between the trolley and the surface is 0.04, so coefficient of kinetic friction is represented by Fk in the figure. Fk acts leftwards because trolley is moving in the right direction. The kinetic friction is left. Fk is left side. And surface it is given as 0.04. What is the tension in the string? So we have to find the tension in the string. This is the string attached to a pulley and a weight 3 kg is attached to which goes downwards. Take G is equal to 10 meters per second square. Neglect the mass of string. Answer. Now we have to resolve the vertical components as well as the horizontal components in the free body diagram. Therefore, considering this figure, given figure, 3 kg is the weight and the tension acts upwards and the downward force due to mass is 30 newtons, and it is given by, it is equating in the equilibrium, vertical force is equal to downward force, that is equal to 30 minus T, because T is acting upwards, that is equal to M into A. Mass of the body here is 3 kg. 3 into 10 is the gravitational force. Therefore, 30 minus T is equal to 3A. By second law of motion of the trolley, now we will have the free body diagram of this trolley. Therefore, Fk is acting leftwards. This is shown here. And weight is here W. And T is acting rightwards. Here W is 20 kgs. So tension is on the right hand side because this string is pulling this side, right side. Therefore, solving T minus Fk is equal to 20 kgs into A. Therefore, now Fk is equal to mu k into N. We know that Fk is equal to mu k into N. And it is given mu k is equal to 0.04 and N is, therefore N is equal to 20 into 10, that is 200 newtons. Thus the equation of motion of trolley is T minus 0.04 into 200 is equal to 20A. Now we have to find the value of A. Simplifying this previous equation, we get T minus 200 into 0.04 is 8 minus 8 is equal to 20A. Let it be equation 2. Therefore, solving for equation 1 and 2, we get, see, if you add equation 1 and 2, you will get 30 minus 8 is 22. T minus plus T and minus T get cancelled. 20 plus 3A. 20A plus 3A is 23A, or simplifying, we get A is equal to 22 by 23 meters per second square. That the value of acceleration, we get 0.96 meters per second square. And we get, substituting the value of A, we get T is equal to 27.1 newtons. We will continue by answering short type of questions. Short answer type of questions. Question 1. A passenger sitting in a car at rest pushes the car from within. The car does not move. Answer. For motion, there should be an external force. Next question. Question number 2. Give the magnitude and direction of the net force acting on a raindrop falling with a constant speed. Answer. As vector A equals 0, F is also 0. That because F is equal to M into A. Question 3. Why the passengers in a moving car are thrown far outwards when it suddenly takes a turn? It is due to, answer is due to the inertia of direction. Question 4. You accelerate your car forward. What is the direction of frictional force on a package resting on the floor of the car? So please note the frictional force on the package resting in the floor of a car. Answer is the package in the accelerated car, a non-inertial frame, experiences a pseudo force in the direction opposite to that of the motion of the car. The frictional force on the package which acts opposite to this pseudo force is thus in the same direction, that is forward, as that of the car. Next question. What is the purpose of using shockers in a car? Answer. To decrease the impact of force by increasing the time for which the force acts. Question 6. Why are tires made of rubber, not of steel? Answer is, since the coefficient of friction between rubber and the road is less than the coefficient of friction between steel and the road. Next question. Wheels are made circular. Why? Answer is, rolling friction is less than the sliding friction. Question 8. If a ball is thrown up in a moving train, it comes back to the thrower's hand. Why? Answer is, both during its upward motion and downward motion, the ball continues to move with inertia of motion in the same horizontal velocity as the train. In this period, the ball covers the same horizontal distance as the train, so it comes back to the thrower's hand. Question 9. Calculate the force acting on a body which changes the momentum of the body at the rate of 1 kg meter per second square. Answer. As F is equal to rate of change of momentum, that is dp by dt, F is equal to 1 kg meters per second square. Question 10. On a rainy day, skidding takes place along a curved path. Why? Answer. As the friction between the tires and the road reduces on the rainy day. Question 11. Why does a gun recoils when a bullet is being fired? Answer. A gun recoils to conserve the momentum. Question 12. Why is it difficult to catch a cricket ball than a tennis ball even when both are moving with the same velocity? Answer is, being heavier, the cricket ball has higher rate of change of momentum during motion. So, cricket ball needs more force. Next question. The distance traveled by a moving body is directly proportional to the time. Is any external force acting on it? Answer is yes. As S is proportional to T, so acceleration A equals 0. Therefore, no external force is acting on the body. Question 14. Calculate the impulse necessary to stop a 1500 kg car moving at a speed of 25 meters per second. So, change in momentum is given by I is equal to m into v minus u, where v is the final velocity and u is the initial velocity. Substituting, we get the weight of the car 1500 into 0. That is final velocity to stop a car is 0 minus initial velocity is 25 meters per second. Simplifying, we get the answer as minus 37,500 newtons. Next question. Lubricants are used between two parts of a machine. Why? It is to reduce the friction and wear and tear. Question 16. What provides the centripetal force to a car taking a turn on a level road? Answer is, force of friction between tires and road provides the centripetal force. Question 17. A body is acted upon by a number of external forces. Can it remain at rest? Answer is yes. If the external forces acting on the body can be represented in magnitude and direction by the sides of a closed polygon taken in the same order. Question 18. Bodies of larger mass need greater initial effort to put them in motion. Why? Answer is, as F is equal to ma, so for a given value of a, more force will be required to put a larger mass in motion. Next question. An athlete runs a certain distance before taking a long jump. Why? Answer is so that inertia of motion may help him in his muscular efforts to take a longer jump. Question 20. Action and reaction forces do not balance each other. Why? Answer is as they act on different bodies. Next question. Question 21. The wheels of vehicles are provided with mudguards. Why? Answer. When the wheel rotates at high speed, the mud sticking to the wheel flies off tangentially. Please note tangentially. This is due to the inertia of direction. In order that the flying mud does not spoil the clothes of a passerby, the wheels are provided with mudguards. Question 22. China wares are wrapped in straw paper before packing. Why? The straw paper between the China ware increases the time of experiencing the jerk during transportation. Hence, impact of force reduces on the China ware. Question 23. Why is it difficult to walk on a sand? Because answer is because of less reaction force. Question 24. The outer edge of a curved road is generally raised over the inner edge. Why? Answer is, in addition to frictional force, a component of reaction force also provides the centripetal force. Question 25. Explain why the water does not fall even at the top of a circle when the bucket is full of water is tilted upside down rotating in the vertical circle. Answer is, the weight of water and bucket is used up in providing the necessary centripetal force at the top of the circle. Question 26. Why does a speedy motor cyclist bends towards the center of a circular path while taking a turn on it? The answer is, it is so that in addition to the frictional force, the horizontal component of normal reaction also provides the necessary centripetal force. Next question. An impulse is applied to a moving object with a force at an angle of 20 degrees with respect to velocity vector. What is the angle between the impulse vector and the change in momentum vector? Answer is, impulse and change in momentum are along the same direction. Therefore, the angle between the two vectors is 0. Question number 28. A man getting out of a moving bus runs in the same direction for a certain distance. Please comment. The answer is, it is due to inertia of motion. With this, we come to the end of answering short answer questions of 1 or 2 marks. We will take up some more examples in our next lecture. In the next lecture, we will study about circular motion, and we will also learn about solving problems in mechanics. We will also solve some 3 marks and 5 marks question and numerical problems. Till then, goodbye.